Okay, so um, I want to talk about what it means to have a limit or to be a limit, and really, I want to make sure that everyone's on the same page from last spring. It's a kind of a crazy end of the year, and so in honors pre-calc, we maybe didn't cover as thoroughly or as rigorously as we've done in the past, and so part of the purpose of this video is to just kind of remind yourself of what a limit is and things that you should know and kind of what the expectation is going into BC calculus. Okay, so what is a limit, right? A limit. I'll dismiss that. That's fun. That's new. So what is a limit? So a limit simply describes. I think I wrote it down here already. A limit describes the behavior of a function near a given point. Okay, and I don't know how long I've had this quote up here, and in fact, if you had me for honors pre-calc, you probably saw the screen, right? I just think it's just very simple, but it explains exactly what a limit is. It's talking about a behavior, right? And a behavior of a function is the y value. So you're trying to figure out the y value of a function, and notice how I put in red near a given point. And so you don't want to be at the point. And a lot of times the point in question could have some problems, right? Could have things that happen that could cause a function to be undefined. Could be an asymptote. Could be a hole, right? Could be a whole bunch of things. So the given point, let's say in this case the given point was 2. If you want to be near 2, that's what we use this notation, this limit as x approaches 2. So we're going to get close to 2, and it's of the function, and whatever the behavior is, it's a y value. So that's what we're trying to find. And part of the rigor in calculus is to determine how close do we need to get. And I think I showed these slides too, in the spring, and so we're trying to get close to 1. So we want to know what's the behavior when x is equal to 1. Well, if you think about this is 1 right here, and so it looks like this, it looks like a sine graph actually, right? I mean, it looks like with an amplitude of 3, right? That if you think about that from last year, but the fact is, this looks like a sine graph, and the sine graph is very predictable. So I don't know what's hiding behind this yellow bar. It's been blocked out. Like there's an interval that I can't see, but just based on what I can see, looking from both directions, looking what's happening from this direction and from this direction, it looks like the function's going towards 0. And so, you might say, well, maybe that's not close enough. Okay. So then you could remove that layer, right? And yay, look at how cool. It's a little bit closer, right? So we're a little closer to 1, right? We're getting close. We're approaching 1. And, it looks like the behavior is the same. And so again, you're like, oh, okay. It looks like we're approaching 0. The behavior of the function looks like it's 0. And, I just had a lot of fun here. So we could get narrower. And again, I'm watching as these arrows, like they're kind of getting closer and closer. The behavior from both sides is getting close to the same value. And we can continue to narrow this width, right? Get smaller and smaller intervals. I mean, that's really close. And look, we're even closer. It looks like that the function is behaving as we predicted it, that it should be equal to 0. And oh, look at that. And right there it is, like right there, as x approaches 1, the y values approach 0. But here's the thing. I really don't need to see that, because a limit doesn't ask you what is f of 1. It says what's happening is you get close to f of 1. So I want to make sure you realize that this is not looking for, we're not looking for f of 1. Okay, that's a separate question. Okay, we're not looking for that. We're looking for what's happening as we get close to 1. Now, these might be the same, like in this case they were, right? The behavior is getting close to 0, but they don't have to be the same always. And then we'll talk about the importance of when is it the same and when isn't the same. Now, again, we are looking here, and it appears like it's the exact same function of a sine graph. And again, we could start to peel off as we get close to 1. what's happening, right? And again, the behavior of our graph, if we, kind of think about that for a second. So the behavior from this side and the behavior from that side, are they, approaching the same value? Are they getting closer and closer and closer to the same point? And again, it looks very similar to the last example that, this is very narrow. Like we have a lot of evidence that the two sides are meeting at zero. You're getting closer and closer and closer because you think about like what's missing here, right? Like this value right here might be like 1 or 0.9999, and this side might be 1.00001. So we're really, really close. So we could say that the limit here is equal to, 0, just like before. And, you might say, well, wait a minute, Mr. Brown, like, I don't know what's happening behind here. And in all honesty, it doesn't matter. A limit doesn't know, or you don't need to know for a limit. You don't need to know what's happening actually at the value. You need to be knowing what's happening as you get close to the value. And if you remove this and you take a look, notice, there was a hole here and the filled in values up there. So there's our function value, right? Our function value, f of 1, is equal to 2. But I'm not looking for f of 1. I'm looking for the limit. So I don't care that f of 1, the actual value is 2. That's fine. This right here is your limit value. Okay, and in fact, had we not seen this, right? Had we not seen that hole, had we not removed this final layer, we would never have known the difference. And that's the whole point of a limit. You don't really want to know what's happening at 1. You want to be knowing, in this case, what's happening as you get close to that value, right? As you get close to 1. Okay, now, another thing that you want to be prepared for when you talk about limits is to be able to analyze them on your calculator, especially on the tables of values. And again, I covered this last spring, and it's something I want to make sure you guys are aware of, that if you have a rational function, so I have x squared minus x, right, minus 2, and then, over x minus 2. So what I want to do, let's see if I can remember how to do this here. What I want to do is, give me a second, because I do have, I'm so rusty on doing these videos. I apologize. Okay, go back to here. So I do have a calculator pulled up here. There it is. Okay. So what I wanted you to do is to type this in your calculator, right? In your y equals x squared minus x minus 2 divided by x minus 2. And use parentheses. Be careful if you don't have a calculator model that actually does the division bar. You want to be careful. And instead of going right to the graph, I want to go to the table of values, but let's go to table setup for just a quick second. So table setup, which is, I think, right there. And we want to start at 2. And, so table setup. So we want to start at 2. And right now, let's change by, 0.01. Okay, or even we can even just do 0.1, I guess, if you want. There you go. Delete that guy. Okay. Now, so that means we're going to start at 2 and we're going to change every 10th. Okay. And so if I do that, if I go to my table, table, notice I do have an error at 2, as I should, because if you think about that, right, the function is not defined at 2. You're dividing by 0, so that's not good, right? So, but if you take a look at after that error, you see what's happening near that. What's happening near 2, right? This is 2.8, 2.9. You could even scroll higher, 2.7. And then, 3.1, 3.2, 3.3. So if you didn't see this error, right, if you could block that out and say, guess what's missing, what should be the pattern, you probably have a logical guess of 3, right? And that's a great guess because that seems to fit the behavior of the values. And if you go to your table setup and you wonder, well, starting at 2, is changing by 0.1 close enough? Should I make it a smaller increment, like every 1/100th, to get a little bit closer? And again, you can go back to your table and you can see that even if you change by 1/100th, you have a really good pattern here, right? 2.98, 2.99. What's missing? And then it starts at 3.01, right? So you do have a good evidence that the limit should be equal to 3. And honestly, like you could go to your table setup, and I think I did this last spring, 0.00, you go 1/10,000th, like, right? And you go back to your table. I don't even know if it'll handle this. Oh, it does. Good. I mean, like, pretty accurate, right? That this limit should be equal to, should be 3. So your calculator in terms of, like a table, it's really nice because if you would have gone just to your graph and looked at this, you're going to be deceived. You're just going to see a straight line. And what you don't see because of the largeness of the pixels is there's actually a hole, right? There's a gap at when x is equal to 2, but the behavior says, hey, the y value should be 3. And because everything else around in that table, if it is fitting a pattern pretty much linearly, then that's going to make sense why that's a line, right? Now, for those of you who remember these kinds of problems from honors pre-calc, you remember that there's things we can simplify with this problem, right? There's a reason why it's linear is because there's a factor, there's something that can factor and cancel, and we'll discuss that and review that in the next video. I think I just did screenshots here. Yeah, right. I just did screenshots so you can kind of see, no matter how close you get, that error, it's still pretty predictable that value should be 3. And, this is where we first introduced talking about a limit. Instead of saying what's happening around 2, right, you're saying the limit as x approaches 2 of this function. Okay, so that's just some kind of basic intuitive ways we can think about limits. And again, my hope and my like from last spring, that this looks familiar to you. And I'll have one more video I'll make just a second, and that'll just review a few techniques that we covered as well in the spring, just to kind of remind you of what you should know in coming into BC Calc.